So we're going to be looking at infinite series day 6, and the test we're going to be concerned with today is what's called the ratio test. Before we get into the ratio test, a little bit of review of factorials because we're going to need these ideas within this lesson. So let's say you have a quantity like this, n factorial over n plus 1 factorial. So most students will note that n factorial is really just counting down, so n minus 1, n minus 2, all the way down eventually to 3, 2, 1. And then n plus 1 factorial, similarly, is n plus 1, n minus 1, all the way down to 3, 2, 1. And you can see that the things that cancel out is everything except for 1 over n plus 1. There's another way to look at this, and that way is to view this n plus 1 factorial as n plus 1, and then the rest of the countdown is really just n factorial, so you can cancel that way. Let's assume you're given the following problem. 2n plus 1 factorial over 2 quantity n plus 1 factorial. So I'm going to leave the 2n factorial alone on the top, and then the bottom I'm just going to distribute the 2, which is something that is commonly missed. So I'm going to have 2n plus 2 factorial. Let's apply the shortcut learned above. So I have 2n factorial over this 2n plus 2 I'm going to rewrite as 2n plus 2, and then 2n plus 1, and then the rest of the countdown will just be 2n factorial. So you can clearly see that I can then cancel the 2n factorials, and I'm left with 1 over 2n plus 2 times 2n plus 1. So with that in mind, let's get to what the ratio test says. So the ratio test is the following. So given an infinite series, we'll just call it sigma a sub n. It could be alternating or it could be all positive. It doesn't really matter. We are going to let the Greek letter rho equal the limit as n approaches infinity of the absolute value of the ratio of the next term over the previous term. We're going to examine what this does. There are 3 things rho could do. The first case is if rho is less than 1. If rho is less than 1, what we're saying is that the bottom is bigger than the top. Or in other words, the next term is less than the previous term. So by the ratio test, that series converges. If rho is greater than 1, what we're saying is the top wins. So actually, the next term is bigger than the previous term, so terms are getting proportionally bigger, so we can show that that diverges. The third case is if rho is equal to 1, then it turns out that it's inconclusive. So we have to apply some other test to deal with that series. So there's the ratio test. The ratio test is typically used if the series contains terms that have factorial, okay, or 2 to the n, anything like that. So if it contains n factorial, 2 to the n, e to the n, or especially if there's a combination of those guys, then it's typically the ratio test that's your best bet. Let's start with our first example. So let's assume our series is sigma n equals 1 to infinity, 2 to the n over n factorial. So this is a good candidate for ratio test because of the factorial, but also because it's in a mixture with exponentials. So we're going to let rho equal the limit as n approaches infinity of the n plus first term looks like this, 2 to the n plus 1 over n plus 1 factorial, all over the original, which is 2 to the n over n factorial. I want us to note that there's actually no negative, so we can do away with the absolute value. So it's the limit as n approaches infinity, and I have 2 to the n plus 1 over n plus 1 factorial times, I'll just multiply by the reciprocal, which is n factorial over 2 to the n. So what can we cancel before we take the limit? Keep in mind from before that n plus 1 factorial is n plus 1 times n factorial, and 2 to the n plus 1 is really 2 to the n times 2 to the 1. So the things that can cancel is the n factorials, which is essentially cancel out the factorial, the 2 to the n's, which essentially cancels out the 2 to the n power. So what does our limit now look like? It's the limit as n approaches infinity. On the top, I'm left simply with a 2. On the bottom, I'm left with an n plus 1. This limit is 0, which is less than 1, so this series converges by the ratio test. Let's look at a second example that's slightly more difficult, but we'll apply the same ideas. So let's say our series is sigma n equals 1 to infinity, and then it looks like this, n squared, 2 to the n plus 1, all over 3 to the n. Let's go ahead and take our ratio test. I note that there's nothing negative, so I don't have to worry about absolute value. So the n plus first term looks like n plus 1 squared, and then 2 to the n plus 1 plus 1, so n plus 2 all over 3 to the n plus 1, times the reciprocal, just to keep things simple. I get 3 to the n, and then on the bottom I get n squared 2 to the n plus 1. Let's take a look at what cancels. The 3 to the n will cancel the 3 to the n. The 2 to the n plus 1 will cancel the 2 to the n plus 1 here, so you're actually just left with a 2 to the 1 power. If you're not sure, just think of it as similar basis, subtract the exponents. So what does our limit look like? It looks like the limit as n approaches infinity. On the top I have n plus 1 squared, and I have a 2 left. On the bottom I have a 3 left and an n squared. Since it's a simple polynomial, I can make an approximation. If I FOIL at the top, I have 2n squared plus some stuff. On the bottom I have 3n squared. So this limit is 2/3, which is still less than 1. So what that tells me is the series converges by the ratio test. For our third example, let's look at a series that is inconclusive and then talk about what to do from there. So let's assume I have this. Negative 1 to the n, square root of n over n plus 1. Okay, now without going through the work, you can actually show that rho is equal to 1, which is inconclusive. So since I don't know what that does, I have to use another test. The most appropriate test for this series would be to use the alternating series test. So let's run through it very quickly as review. The first thing I'm going to do is take the limit as n approaches infinity, ignoring the alternating part. And you can see the bottom is bigger than the top, so this limit will be 0, check. And then without too much work, you can show that the next term is in fact greater than the previous term, check. So although the ratio test was inconclusive, this series in fact converges by the alternating series test. The last example we'll look at is going to be more difficult, but we want to look at some of the details that you have to watch out for. So let's assume I have n to the n over n factorial as my series. So I go ahead and I find my rho. So rho is equal to the limit as n approaches infinity. Again, no absolute value needed. I have n plus 1 to the n plus 1 all over n plus 1 factorial times the reciprocal of the original, n factorial over n to the n. So let's see what cancels. Again, we know that the n factorial will cancel the factorial, and that seems to be all we can do. So what I'm left with is the limit as n approaches infinity. I have n plus 1 to the n plus 1 on the top, and on the bottom I have an n plus 1 and an n to the n. Now notice the n plus 1 is n plus 1 to the first, so that can actually cancel that. So we're left with the limit as n approaches infinity, n plus 1 to the n all over n to the n. Now it's tempting at this point to ignore the plus 1 and say this limit is 1 and it's inconclusive. However, because it's not a polynomial, it's kind of sketchy to do that. So let's go ahead and go through the work. What is helpful in seeing this is to pull out the to the n power. So you're left with an n plus 1 over n. If you take the limit, a lot of students will recognize that, hey, this is 1 to the infinity, which is indeterminate. So L'Hopital's will apply, and you'll have to do some natural logs, things like that. If, however, you divide through by that n, or split the fraction, you get 1 plus 1 over n to the n power. It still looks like it's 1 to the infinity, but some students will recognize that this limit is e, which is greater than 1. So this series, in fact, diverges by the ratio tests. Here are some of the practice problems we did in class. I'll give you the solutions, but the details is really important to work out. The first one was convergent by the ratio test. The second one, also convergent by the ratio test. Third one is convergent by geo. You can actually split up the series, and you can see that both are convergent geometric series. The fourth one is divergent. You can use either integral test, comparison test, or limit comparison. The fifth one is divergent by divergence test, and the sixth one is also divergent by divergence test. You could use ratio test, but it is a lot of work.